We're going to start really getting into geometry, looking at points, lines, and planes today. And then we're also going to look at angles. These are kind of the foundational tools of geometry, the things that the building blocks of geometry. Geometry really is looking at different types of shapes and different characteristics that they have. And so we're going to start out here looking at getting some definitions of these things. First of all, points. Well, points are like a dot, right? And the dot that I drew up here, I don't know if you can see that, has some thickness to it. But in theory, a point doesn't have any thickness to it. So this is maybe even a poor representation of a point. A point is smaller. It's infinitely small, or infinitesimally small. I don't know how to say the word. But it's so small, you can't see it. It has no thickness to it at all. It is what we call a zero-dimensional object, right? There's basically no thickness. Oop, I can't spell. No thickness. It is zero-dimensional. Okay, zero-dimensional. There's no, there's no thickness in any direction. Okay. Lines are different. Lines consist of points, an infinite number of points, that extend indefinitely in one direction. Well, kind of two, but opposite. One dimension, I should say. So there's no thickness to this, but there is length. Okay. No thickness. So again, my marker as I draw this has some sort of thickness along that line, but in theory, the actual line has no thickness. It's just a string of points that it extends indefinitely in one dimension. So no thickness, but infinite length. And it's considered one-dimensional. Okay, one-dimensional. It's a one-dimensional object because it extends in one direction, kind of two directions, but opposite. Okay. It's also made up of an infinite number of points. Okay, made up of infinitely many points. Now, a plane has both length and thickness. Okay, well, I shouldn't say thickness. Maybe thickness is the wrong word. Length and width, right? It's got two dimensions to it. It extends actually in an infinite number of directions, right? So there's a direction, there's a direction, there's a direction, an infinite number of directions, but two dimensions. Okay. But there's no thickness in the sense that, like a sheet of paper kind of is like a plane, except that there is some thickness to it. I've got a whole pad of graph paper here, but there is some thickness to a sheet of paper, but a plane has actually no thickness. Again, the thickness in all of these cases is zero. So no thickness. It is infinite in size, I suppose you could say, because it extends indefinitely in all directions. Okay, in size or area, could call it area. It's the amount of space taken up by the plane. It just extends indefinitely. Now when we draw it, we typically draw edges. Okay, I could draw it with 4 edges. I could draw it with 3 edges if I wanted to. But we assume that those edges aren't actually the boundary of the plane. Planes don't have boundaries, neither do lines. They extend indefinitely. They're infinite in size. We consider them two-dimensional. They have infinite length and width. Okay, so the size here length and width. Okay, going in both, both dimensions. And it is made of infinitely many points, but also infinitely many lines, right? You could line up an infinite number of lines here and still get a plane, right? So it's made of infinitely many lines. Okay, so just some characteristics of those three sort of building blocks of geometry. Okay, when we start putting these together and looking at restricting them down a little bit, we'll get some even more definitions in there. So, for instance, lines. Lines are great, they're infinite in length, but sometimes we don't want all of that length. Sometimes we want just a portion of it. And so you can have what we call half lines. That's another possibility. Half lines are basically a line, if you pull a point out, it splits it into two half lines, right? So it's like it's what you would get if you take a point out of the line, you end up with two half lines going either direction. And so we kind of represent it this way. It's an open dot on one end, and then the other half is the line going off. Okay. Similar features to lines. It is still infinite length, even though it's half the length, right? Half the length of an infinite thing is still infinite. But we don't include the endpoint. Okay, we don't include that endpoint. However, a ray is where we do include the endpoint. It's like the half line with the point back in. Okay, so a ray. Funny looking Y there. A ray is like the half line with the endpoint included. So we do include the endpoint on a ray, all right? So just a couple little definitions there that kind of play in. Now, if I combine rays, I can put two rays together and I get something called an angle, okay? And these are again the building blocks of geometry. Angles are very important when we start looking at shapes. So angles are basically two rays with the same point. They kind of intersect at the end point. So right, so kind of something that looks like this. It's technically two rays with the same endpoint. Okay, two rays with the same endpoint. Now, what's neat about angles is that they apply to many things. We can look at angles with different shapes, polygons, things like rectangles and pentagons and triangles. We can also look at angles with circles. We can look at angles of the way that planes come together. They come together at angles. Angles are very important. It just represents the different relationships, sort of the tilt or the bend between two different objects, which is kind of interesting. Now with angles, we measure them. This angle here might be bigger than this angle. The opening can be measured, okay? Whereas both of these are smaller than an angle that might look like this, okay? So angles can be measured or quantified in some way. And so the way that we do that is we define a unit of measure called the degree. And there's actually others, radians, that we don't talk much about or at all. But degrees are important. They're very practical, and you'll see that show up. So the way that we get degrees or define them is we take a circle and using the center as the shared endpoint on the rays, we split the circle into 360 even pieces, or equal sized pieces, I should say. And each of those 360 pieces, 360 equal pieces, and of course that the one I drew is probably bigger than 1 degree, but each of them is considered 1 degree. Okay, each piece is 1 degree. Okay, so 1 degree is essentially 1/360th of an entire circle. Okay. In fact, running out of space, so I'm gonna erase a little bit here. So 1 degree is equal to 1/360th of a circle. Okay, that gives us at least a unit of measure with which to work with these, to compare them. Okay, we represent a degree using this little superscript 0, just like we do with degrees Fahrenheit and Celsius, right? Same sort of notation there. And and then with angles, we name the different parts. So the shared point, the shared endpoint is called the vertex. And then an angle, you kind of think about a ray that kind of swoops across the angle from start to finish. The starting ray, the initial ray where it starts, is called the initial ray. Use the word. Initial ray is where it starts, and the terminal ray is where it ends. Okay, so initial and terminal. And so the portion of a circle that's swiped out by that ray is measured in degrees. It's the number of 360ths of a circle that is swiped out. Some really important angles. If you take a circle and you imagine cutting it into quarters, well, what's a quarter of 360 degrees? 90, right? And so a quarter of a circle is 90 degrees. An angle that is 90 degrees is called a right angle. So any angle that is a right angle is 90 degrees. And any angle that's smaller than 90 degrees, so something in there, is what we call an acute angle. Those are less than 90 degrees, okay? Or really, I should say they're between 0 and 90 degrees. Yeah, I'll just say less than. I don't have a variable up here to stick in an inequality, so I'll just say they're less than 90 degrees. Good enough. You know what I mean. Okay. A 5-degree angle is acute. An 82-degree angle is acute. Okay. Obtuse angles are ones that are greater than 90 degrees. However, they're also less than 180. A 180-degree angle, which is half the circle, goes all the way around, or half the way around, sorry, all the way to the other direction. Those are called straight angles. Straight angles are equal to 180 degrees. Okay, so equal to 90. There we go. All right, so that gives us some definitions there. So anything bigger than 90 is obtuse, anything smaller than 90 is acute, and then 180 is straight angle. Okay, now what's interesting then is that if you take a straight angle, this is kind of neat. Take a straight angle, well, that's actually just a line, right? Throw a point in there, and that's two rays. There's infinite number of points, just pick one. And so a straight angle is a line. And the angle measure is 180 degrees for a straight angle, okay? That's half your circle, half of 360. Okay, now if I had, let's say I had a straight angle, and I had another ray shooting off. So now I've got three rays creating two angles, okay? Maybe I'll call these angle, I'll give them some names. In fact, naming angles is very important. There's many ways to name angles. One of them is you could stick a number there and call it angle, and the representation for an angle is kind of this little shape. It looks like an angle. And then some textbooks will actually just leave it like that, and some will put a little arc through it. Our book uses the arc idea, so this is angle 1 and angle 2. All right, so those are angles 1 and 2 there. Sometimes we use points within the angle or on the rays to define them. And so, if I were to, instead of 1 and 2 here, if I were to have points A, B, C, and D, for instance, you can define the angles. I'll leave the 1 and 2. Why don't I leave them? Angle 1 is the same as angle ABD, right? So I'd say angle ABD is the same as angle 1. Those two are the same. And in fact, I could even write that in reverse, angle DBA. Those are all the same. As long as angle B is the vertex, that's the middle one. So the middle letter used is the vertex letter, okay? So the middle letter is the vertex of that angle, okay? And then angle 2 here, just kind of drawing around stuff, angle 2 would be considered CBD or DBC, either way, okay? So angle DBC, same as angle CBD, all right? Yeah, okay, so that gives you kind of an idea. That D looks horrible there. Gives you an idea how to label and measure these things. In addition to that, with a straight angle, angles 1 and 2, or whatever, however you want to label them, are what we call supplementary angles. Their sum is 180, okay? Individually they aren't, but together they make a 180 or a straight angle. All right, so supplementary angles they sum to 180 degrees. Okay, so you add them up to get 180. So in this case, I would say that angle 1 and angle 2 are supplementary. Okay, and if I knew one of them, I could find the other by subtracting from 180. For instance, if I assume the measure of angle 1 is, let's say it's 100, 30 degrees. Okay, and when we say the measure, that we're going to abbreviate that with an M in front of the angle. So the measure of the angle is what the number of degrees. Then the measure of angle 2 is 180 minus that 130, right? Because the two together have to make 180. So if you subtract one off, you get the other one. And that would be a 50-degree angle then. Okay. So together they have to make 180. And that makes sense because 130 and 50 make 180. Okay. Okay. So it gives you an idea of how we label things, the supplementary idea, and then there's also something similar called a complementary angle. Complementary angles add up to 90 degrees instead of 180. Okay. Now I don't have an example up here, but just in general. Complementary angles, they sum to 90 degrees, okay? All right, so again, you just add them up to get 90, or if you know one and you don't know the other, you subtract it from 90 to get the other, okay? All right, so that gives you just some definitions here. Let's say for a moment that we had two straight angles that kind of ran through each other. Essentially, you have two intersecting lines is what you end up with there. Oops, let's go with blue. Oh, my blue is dying on me here. So here I have two straight angles. They intersect at the same vertex. And I'll throw some numbers up there just so it's for ease of labeling. Angle 1, 2, 3, and 4. Then vertical angles are the angles opposite each other. Okay, so vertical angles are opposite each other. So in this case, angle 1 and angle 3 are vertical angles, and angle 2 and angle 4 are vertical angles. And what's neat about vertical angles is that they're always equal to each other. And the way you can figure that out, you can kind of deduce that using the idea of supplementary angles and kind of equating some things. Basically, angles 1 and 4 are supplementary, angles 1 and 2 are supplementary. So both of those sums are 180. If you take angle 1 off of that, it leaves two remaining equal portions from that 180. Okay, so and then you can kind of work that similarly around for all the different comparisons. So that would leave angles 2 and 4 congruent, or congruency is the same as having the same measure. In fact, maybe I'll mention that or define that. So angles are congruent when they have the same measure. Let's put that up here. Get rid of that blue marker. Angles are congruent when they have the same measure. Okay. And so in this example here with the vertical angles, I could even pull out the congruent angles. I could say that the measure of angle 1 is equal to the measure of angle 3 because they're vertical angles. That also means that angle 1 is congruent. And congruent, we use a slightly different symbol. It's like an equal sign with a little squiggly on top. Okay, we say angle 1 is congruent to angle 2, or I'm sorry, angle 3, good grief. There it is. So if the angles have the measures that are the same, then they are technically called congruent. The angles aren't equal because the angles could be different. I could have an angle over here and an angle over here that have the same measure. They're different because they're made up of different points, made up of different rays. So I can't say they're equal angles. They have equal measure, which means they're congruent. They're the same size. Okay. So we just use a different term. We use the word congruent to represent same size, not necessarily exactly the same points and rays and everything. Okay. Okay. And so, yeah, I think what we'll do is I'll move on to another video. The next video I'll talk more about parallel lines and how we can find angle measures based upon some assumptions dealing with parallel lines.